So as Brian said, what I'm going to talk about in this presentation is about some of the things that are important in the context of providing scalable HPC communication capabilities. So let's move things forward. So to frame this discussion, I mean, really need to put in context the sort of problems that need to be addressed, the problems that need to be resolved, and so the slide here gives a summary of the challenges facing us as we move towards exascale, and on the right hand side, and on the left hand side, what the impact of this would be on solutions, or the challenges that face providing scalable communication capabilities. And these are really things that have come from multiple studies. This is nothing original. There have been multiple studies on what things will look like at what people think things will look like at exascale. So first of all, there's the fact that the assumption that there will be a very large number of computational elements that could be producing data, and of course the first requirement here, which is an obvious one, is the need for having scalable communication capabilities, which translates itself throughout, not just in terms of implementation, but also when you look at standards or APIs. There's an impact on those APIs if they're going to be usable at large scale. Large on-node functional unit count. Again, depends on how you count. How do you count a GPU? Is that one endpoint, or is that several thousand, or if you're talking about NVIDIA GPUs or something like that? And again, here there's tremendous impact on the sort of capabilities that a card that's generating data, or that's putting data on the network has to support. Has to be able to be very scalable in terms of a single functional unit. Has to be able to service a lot of endpoints. A lot of sources of data or destinations for data at the same time. Deeper memory hierarchies, something was brought up today, leads to a need to be better integrated within the memory hierarchy, especially as with a very large number of endpoints. Latency is much larger. Much larger problem, and so having the ability to, inject data into the appropriate cache, for example, rather than into memory and then pull it in, it becomes very important. Smaller amount of memory per functional unit puts constraints in terms of implementation on how much memory an implementation can really use. For communication, especially when the application wants all the memory that's there. There's issues around data heterogeneity, which leads to need to support heterogeneous data in a good way across the fabric. Dealing with failure, trying to optimize data movement. A thing that's coming up recently more is or at least I see this more with things like SHMEM in particular, is the need for SHMEM as a representative of PGAS languages, is the need for very good independent remote hardware progress, independent of a user context or something like that. And of course, power is a challenge for everyone, and so these are some of the hardware side factors that affect what communication look like, and really are what drive a lot of the work that's being done for developing new communication capabilities. I call it a few things here that focusing more on user-side APIs, specifically MPI, but SHMEM is no different than this. I mean, both standards face these same problems, although of course, some are appropriate for one and not for the other. But the need for truly asynchronous communication capabilities is obvious, especially if applications really are going to have to work on very small quantities of work and very efficiently. The need to overlap communication and computation just to be able to get some reasonable utilization out of the system requires this sort of support, so you can have good overlap of computation communication. Really need remote one-sided progress. That is, if you're doing things like put or get, you really don't want to have the remote side be involved at all for a variety of reasons. Dealing with issues around system noise, there's a very good opportunity with the source of the problems for many of the problems as they affect the applications with system noise is really the use of collective communications. And so a communication stack that can deal with these sort of things helps. And then the topology awareness becomes very important. There are big potential gains to be made if you take in performance and in other aspects if you take topology awareness into account. And so one of the themes that's been come out several times today is the need for open standards. And so really what I'm going to talk about for the rest of the presentation, or most of the rest of the presentation, is the work that we do at Mellanox around moving the InfiniBand capabilities forward to better and better meet these requirements. And so there's standardization both at the hardware level, which is what the InfiniBand standard defines, so that you can have interoperability between different implementations of the same capability, whether it's completely independent runs or if it's a mixture of hardware between endpoints. And of course, it goes without saying that the communication standards that are used today by application developers are open standards. MPI, SHMEM seems to be picking up momentum in some areas. And so the first focus, of course, is, the main focus here is on speed. We really want communications to be very, very fast. As Scott talked about earlier, we as a company are moving forward in a very methodical way, increasing the speed capability, the network capabilities over time, and are focusing right now on the 100 gigabit per second scale. But this is part of a long-term march forward in terms of capabilities, a consistent and long-term march forward. Scott talked about ConnectIB already this morning, so I won't dwell on the details here. But ConnectIB here is in the context of this presentation, ConnectIB is raised because it provides some of our some of our attempts to approach some of the harder problems when it comes to scalability of communications. Dealing with things like very high message rates, which you need if you're going to generate a lot of data on the network from a single source, from a single node. but also scalable transport, which is the dynamically connected transport, or DC. And I'll talk a bit about it. We've also seen the slide on performance here, so let me move really quick to scalability. So one of the things that affects scientific computation, in particular, the performance of scientific computations more than other types of communication is collective communications. Collective communications form often are the factor that determine both the scalability and the overall performance of an application. And so providing very good performance here is of utmost experience. And so this starts with capabilities at the hardware level to provide these capabilities. So InfiniBand provides hardware multicast, which has extremely good performance and is very appropriate for some sort of collective communication. We provide the ability to manage all communications at the network level without the need for CPU intervention, which provides for a good mechanism for avoiding effects of system noise, being able to progress communications very rapidly as data comes in, and not have to have a thread that periodically polls for things. Being topology aware is also very important, and this is one of the areas that we put a lot of work into in our collective communications libraries, and also developing scalable algorithms that scale not just in terms of their performance, scale well not just at 100, 200 nodes, but also at 100,000 nodes, and those are very, very different requirements. And those are the sort of things that we work on day to day. Dynamically connected transport is a transport that's designed to scale well, both in terms of performance and resource requirements, and is really an attempt to our first step towards providing a scalable transport capability. So DK this morning mentioned briefly in his talk, and I would urge people to go and listen to his paper, where he gives actually a lot of details in the work that they did. To implement MPI on top of DC. So DC is a transport that is an asymmetric transport. It has the concept of an initiator of data and a target for data, and so from a single initiator you can send data to any other target. So it's very similar in that sense to unreliable datagram, in that with UD you can send data from a single Q pair to any other Q pair on the host. The main differences between DC and UD is DC, first of all, is a reliable protocol, and so there's no need for software intervention to deal with lost data, and it also supports RDMA and atomic operations, which UD doesn't in hardware. What DC relies on is the observation that a given end node, regardless, can generate data or receive data at some sort of upper limit, regardless of the environment that it's running in. So if you think of the 137 messages per microsecond that a single card can drive at a time, a card can't drive any amount of data faster than that. And so what this has is it has a model of data sources your initiators, and a target that manages receive resources. And the goal here is to keep, to have enough of those resources so that you can satisfy full wire speeds. And what you have is you have basically a pool of resources, or a pool of connections that you basically share over time. It's sort of a set of resources for rent, if you want to look at them that way. And in the resource, and all those resources are managed by hardware based on actual communication requirements as the job is progressing. And so from a resource perspective, really the memory footprint for DC is independent, or nearly independent of the size of the system, as opposed to other InfiniBand-based transports that have come over time that still have a dependency on the size of the system. And again, if you from a cartoon perspective, if you think, for example, of RC, if you really want to use the RDMA capabilities and that the network provides and the like, then if you think of an all-to-all type of communication mode, you have a very, very dense set of connections on a host. Whereas if you with dynamically connected transport, the cartoon isn't working properly. This actually is supposed to be an animation that where the connections change over time, really based on the requirements of the application. So that's one aspect of the work that we've been doing in terms of scalability of communication. Some of the other things that we do is we have support for multiple topologies. So people will use different topologies and different times depending on a variety of reasons. Whether they're the characteristics of their application, whether it's how much money they want to spend on an interconnect or something like that. And we support, we have support for a long time, fat tree as well as multi-dimensional tori. And are adding support for Dragonfly Plus, a variant that differs from Dragonfly that other people you may be familiar with from other sources, in that the subgroup there is based on a fat tree and not based on something like a 2D flattened butterfly. It has characteristics that really help in terms of scale, in terms of performance, and we're also adding support for InfiniBand routing at the hardware level, so that you can provide both network isolation, but also it also is a way to deal with scalability. And also support quality of service, of course, and we'll continue to do so. So you can separate. You can really treat different. You can prioritize treatment of communication over for different types of communication. That's actually one of the advantages of Dragonfly Plus over Dragonfly is it provides more levels of quality of service. You can, and in terms of the other piece that we do is also support InfiniBand over distance up to I forget if it's 60 or 80 kilometers today. So being able to use the native InfiniBand and gain from all the pluses that being able to place data directly where you want it or get it directly from where you want it. In terms of offloading capabilities, so we focus on offloading capabilities really as a way to basically leave the CPU as much as possible for computation. And in parallel, progress communication, really independent of the communication. And so I mentioned briefly, or I will mention briefly, the support that we have that's called Core Direct, which provides the means necessary to offload, for example, collective communication management. A brief cartoon here about the intent behind the Core Direct capabilities. So I have a cartoon here on the left of data patterns for a data pattern for one type of collective communication. In this case, it happens to be a fan-in, fan-out type of data exchange. The main point here is there's the collectives, for example, can't progress until in this particular example, until, for example, rank 0 has gotten data from certain number of sources of data, and it really and so there's explicit coupling between processes in the collective communication and so if you get slowdowns in the communication from system activity, that slowdown propagates itself throughout the entire application just because of the nature of collective communication. If you're able to offload collective communication management to the network, then the system activity which has to happen does not and it's managed on the network and not on the host doesn't affect that particular collective operation, and therefore you get much better scalability and less effective system noise. So in terms of Core Direct takes advantage of the observation that collective communications are really described as a list, described locally as a list of operations between several different endpoints. And so this is described here graphically for some hypothetical for process type of interaction. And so in Core Direct, what one does is one describes this task list, feeds it, gives the whole task list at once to the HCA, and then basically comes back when the results are necessary to check and see if this entire operation has been completed. And so what was done to make this capability work is there's some synchronization capabilities that have been added to the card to synchronize activity between independent queues. So you can wait on data completions from one queue before you progress your own queue, and then the ability to compute data on the card. So you can also do data manipulation on the network without having to use the CPU. And so this is one of the important capabilities that's been added for scalability. Let me skip some of the slides because I'm short on time. These are measurements done several years ago on the ability to really offload collective communication, and we can see here that and provide true asynchronous progress. And so you can see here very good asynchronous progress when you rely on when one uses Core Direct capabilities, whereas if you're relying on the CPU to make the progress, of course, until you get access to the CPU, there's no progression. Another thing that's been done recently is really in an attempt to be able to let the hardware manage the use of non-contiguous memory in a better way. We've added a capability called user-managed memory registration, or UMRs. And what these do is let the, instead of having the memory description rely on scatter-gather entry list like it is in the current InfiniBand spec. This extended the definition of non-contiguous memory to memory keys, and so anywhere you can use a memory key, you can take advantage of. The hardware will handle the any non-contiguous memory aspects of these communication. So this and the place where this is probably most relevant if you're trying to do an RDMA from a non-contiguous region to a non-contiguous region. So you can do those asynchronously using these capabilities. And so there are two types of memory keys that are defined today. One is very similar to the scatter-gather entry list, where you take elements where you arbitrarily combine contiguous regions of memory to describe a new memory key. There are no alignment requirements here. There's and the like, and no length requirements. So you can even do 1 byte, 1 byte, 1 byte. And also the ability to interleave, first of all, to take non-contiguous memory. So memory is contiguous in this direction. So you can take non-contiguous memory and send it in a single description, or you can interleave regions of non-contiguous memory. So this capability, for example, is very important in storage optimizations. For example, if people are familiar with T10 diff, for example, this is the UMR capability is a core to our support for our new support for those capabilities. We're adding support for on-demand paging, taking away the need to intercept memory activity to be able to manage registered memory, and with the ecosystem for processing elements growing rapidly, as was mentioned earlier today, from what initially was one that's based mostly on x86 type of operations of CPUs. Now coming into the market, again slowly, but there are more accelerators, and as power, the Open Power Consortium was announced a while back. So power is becoming more of a CPU to be used. And ARM now, of course, there's a lot of talk about ARM. So our ecosystem is also growing to deal with that, and we support all those processors. We have systems that support those. GPU Direct, we've talked about that earlier, so I'll skip on that. What I wanted to mention very briefly as I close is support that we've added for T10 diff, offload support for T10 diff in our hardware. So for those of T10 diff is a mechanism that's used in block storage to provide data protection. And since I have very little time, all I'll say at this point in time is that our hardware can either work with memory that includes T10 diff and includes the protection data. Data that doesn't include the protection data, it can validate protection data. It can generate protection data when it doesn't exist. as on the fly. It can strip off protection data and the like. And this is capability that we provide right now. So we're, in a nutshell, looking at a lot of different areas on what's missing and what's needed moving forward for providing better support for HPC computation, not just traditional point-to-point, things things like point-to-point communication, but also things that impact storage, impact the processors that are being used, and the like. So that's all I have for now.
Any questions for Rich? Okay. Thank you.
Okay.